All right, it's 8:30, so let's go ahead and get started today. So good morning, everybody. How's everybody doing on this week 4 Wednesday morning? Hopefully everyone's doing well. Hanging in there?
Yeah, doing our best. I think the ash is affecting my eyes now.
Oh,
Getting
yeah.
watery.
Oh, man. Yeah, it's tough going outside. Definitely, try to take care of yourself, stay indoors, and try to stay healthy during this time. Okay, so the plan for today is we're going to continue on with the lecture notes on Bernoulli. So hopefully we'll get through a big chunk of that. And then besides that, I know that there's a lot of questions on problem 3B on the homework. So I'm going to go over a little bit of that at the beginning of lecture today. Mostly just to help you guys out with the geometry, just because I think it's a little bit tough to figure out what's kind of going on with that. So that's my plan for today. But besides that, are there any questions that I can answer about the what we covered last time, or anything about the homework? Okay. So if there's any questions, definitely feel free to stop me anytime. Turn on your mic or send the questions to the chat. I'm always happy to answer. Okay. Okay. So let's go over 3B just kind of really quickly. So 3B. It's a question that has to do with hydrostatic forces on surfaces. Okay? And then what it's asking you to do is basically to repeat part A of that problem, but with an angled gate. Okay? And so just to kind of refresh your memory, so the whole idea with this problem is that you have a gate that's submerged in water. Okay? And so there's a horizontal portion of the gate. Right? And so in part A, there's a vertical portion of the gate that goes just straight up. But then in this problem, I'm saying that the gate is instead angled with respect to the horizontal at an angle of 45 degrees. Okay? So here we have the water, and then this angle right here is 45 degrees. Okay? And so what I'm asking you to solve for is the height, h, that you need in order to hold this gate in equilibrium. Okay? Okay. And so the other piece of information that you need is the fact that there is a pipe. It has some diameter. Okay. And then there's a length L that goes from the middle of the pipe to the hinge. Okay. And so for part B, the horizontal part of the plate is exactly the same. So you can actually use that same answer that you got over in part A. So it has the same moment of it has the same moment, has the same force magnitude, same location, same everything. Okay? And so the only thing that we're going to worry about in part B is recomputing the force on this guy right here. Okay. Okay. And so all of these hydrostatic force problems are the same, in that the two main things that we want to solve for are the magnitude of the force and the location of the force. Okay. Okay. And so we're going to use basically the same formulas and the same methods that we went over in the class, just apply to this angled gate. Okay. And so the in-class example that's probably the most similar to this is the circular gate problem that we did, which was angled with 60 degrees. So we're going to follow that same process. Okay. I think the only thing different is that we're given slightly different variables here in terms of that, but we'll go over that. Right? All right. So first, let's find the magnitude, because that's usually a little bit easier to find. Okay. And so for the magnitude, we have this formula here. So we have, I'm going to call F angle, F ang, right? And so this is going to be equal to the density times gravity times the height of the centroid times area. Okay. And so the two key things in this formula that probably is going to be different from the other one are the height of the centroid and the area. Okay, so let's break this down. So let me redraw this guy right here. So we have an angled gate, and just by the parallel line theorem, or whatever it's called, we know that this angle right here is 45 degrees. Okay? And we know, just from the geometry of the problem, that this this height right here is h. Okay. you can finally finish drawing the triangle just like that. Okay. And so since this is a 45, 45, 90, we can say that's also 45, and this is also 45 degrees right here. Okay. Okay. And so the height of the centroid. So if we go halfway down this slope right here, okay, you go halfway down, right? And if we look at just the height of this centroid, then we know that this is still h over 2. So this hc right here is still going to be h over 2, right? So even though we have an angled gate, the actual depth of the centroid itself is different, or is still the same, sorry. And so, you know, when you're doing these problems, you have to keep in mind that whenever you see h means depth. So depth is just the vertical distance down. So even though we have an angled gate, the depth of the centroid is still going to be the same, okay? And so now let's look at the area, okay? And so the area is going to be the length of this entire plate right here, the whole length, multiplied by its width into the page. Okay? So the width is still the same. So the width is still going to be W, which was given to you in the problem. The thing that's going to be different here is the length, right? And so if we go by the geometry of this problem, we can see that the dimension that we know is actually this vertical plate, this vertical face right here, right? And so the length of this hypotenuse is just going to be h divided by sine of 45, right? And so, you know, that area is going to be slightly bigger than what it was in the vertical case, because as we angle the gate has to be naturally longer in order for it to still reach up to the surface of the water, okay? And so this is going to be hw divided by sine of 45, okay? And then you can plug in all the numbers, and then you get the answer. So the force actually is a little bit bigger in this case than the previous one, mostly just because the area itself is bigger. So the pressure is the same, but since we have a bigger area, our force magnitude is going to be slightly bigger. Okay, right? Does that make sense to everybody? Any questions on that? Okay. Okay, so now let's look at the location. Okay. And so we know that our formula for the location looks like this. YR is equal to IXC divided by YC A plus YC. Okay. Okay. So there's kind of a subtle thing here that I think can be really, really tricky. So the key here is the fact that we're not working in H anymore. So remember, H is depth, but Y is something different, right? So Y is distance along the plate. Okay. And so this is different than the depth, because the plate can be angled at any arbitrary angle right here. And so the Y direction is going to point along that plate. Okay. Okay, so in this case, we have a plate that's angled like this. Okay. And so the Y direction doesn't go vertically down. The Y direction goes like this. Okay. And so you need to be careful when you're setting these guys. Okay. Right. So I won't do the whole thing for you, but I can at least tell you what to plug in for all of these, right? And so we have three basic variables in this formula. So we have YC. Okay. So YC is basically the length along the plate that gets you to the centroid. Okay. So it's basically, you know, we have the centroid that's going to be right in the middle of our plate, and then YC is going to be the distance between here and the surface of the water along the plate. Okay. And so we know from the previous problem that the depth of the centroid is still h over 2, right? Okay. So that's that distance right there. Okay. And so the way that we compute YC is we're just going to use trigonometry again, right? So we're going to draw this triangle right here. Okay. And so we know that the depth or the vertical part of that triangle is h over 2. And so in order to get this distance right here, which is going to be YC, then the way that we're going to do that is h over 2 divided by sine of 45, right? Okay. Right? And so A is going to be the same as before. So A is going to be HW divided by sine of 45. Okay. And so we found that out in the previous one. All right, so now let's compute the moment of inertia with respect to the centroid of the plate. Okay, and so this one's going to be slightly different too because you know we have a different geometry here. Okay, and so normally what this is 1 over 12 times the one of the lengths of the rectangle cubed, which is the one that it's going to be rotating about, times b. Okay. And so we know in this problem that, or at least from part A, that our B coordinate is going to be given by W. Okay. And so our A coordinate here is going to be slightly different because of the geometry. Okay. So we're going to have something cubed, right? And so probably what you did in part A was you did h cubed, right? Because h was the dimension of the rectangle of the plate going that way. But here we have a different length. So instead of h, we do h divided by sine of 45. Okay? Because that's going to be the overall length of this plate right here. So that's going to be h divided by sine 45. Okay. Okay. And so you can see when you have these slanted plate problems, the geometry gets a little bit tricky. But as long as you kind of keep drawing your triangles and keep just double checking every single length, like is this actually the length or is this the depth, then you can kind of work through these problems. So that's kind of the key with these problems is just keeping the geometry straight and making sure you're using the proper lengths in the right places. Okay? And so if you plug all those in, you'll be able to solve for h just like you did in part A. Okay. All right, any questions on this?
Yeah, for the I'm sorry.
Go ahead.
For the YC, you set that equal to h over 2, and you're multiplying the denominator with sine 45 as well.
Yes.
How come? Are you also drawing a triangle with a similar triangle alongside the YC?
Yep, exactly. Yeah, so that's this triangle right here. And so we know that the depth of that centroid is h over 2. And so in order to get the hypotenuse, which is the length that we want, we do h over 2 divided by sine 45.
Okay, so basically we're just creating a similar triangle, just small wise. Since we have the angle, we just utilize that for that part as well, right?
Yep. Mm-hmm.
Okay.
All right, question in the chat. So if you solved it by doing it in terms of YC, would that be okay? Yeah, I mean, if you're getting the same answer, so I mean, the h and the y's, they're going to be different. But just make sure that you're computing things like as long as you're computing the moments, correctly, you're doing the force multiplied by the distance, then you can do it however you want. Yep. So question: how to get h over 2? Yeah, absolutely. So in the formula for the location of the hydrostatic force, we have these quantities here, YC, where YC is the distance along the plate that it takes to get to the centroid. So basically, whenever you see C there, C stands for centroid. So the way that I compute this, because before we actually did this, we have a plate like this, and we have the centroid, right? And what we want to compute is this distance right here, that's going to be YC, right? So I don't know that right off the bat. But what I do know is that the depth of the centroid from the surface of the water, this is going to be h over 2. Okay, and so the depth, that's where I get the h over 2. Whereas the depth of the centroid is always going to be whatever the total depth is divided by 2. Yeah. Okay. Okay, so let's move on. So that was 3D, so hopefully that, that clears things up a little bit. Right? And so let's go back to our regularly scheduled programming about Bernoulli. Bernoulli equation. Right? People in fluid mechanics, we just shorten it to Bernoulli a lot because, you know, it's such a ubiquitous kind of equation. But it's, you know, when I say Bernoulli, I mean the Bernoulli equation. So Bernoulli was an actual dude, you know, very smart dude, obviously. He came up with this equation. But whenever I say Bernoulli, I just mean the Bernoulli equation. Okay, so where we left off last time was we had our fluid particle, and it was in the shape of a box, right? Obviously, you have to suspend your disbelief a little bit because, you know, fluid particles aren't actually a box, but the geometry makes it convenient for doing science. Right? Okay, and so first we know the dimensions of the box. So we know it has a length delta S, and it has a height of delta N, right? And it also has a width of delta Y into the page. Okay. Okay. And in addition, what we know is that there's a pressure P that's going to be at the centroid of the box. Okay? So that's just the pressure that this fluid particle is experiencing. Okay. And so the reason, if you remember from Monday, the reason I give these, I give that length in the delta S is that this particle is riding along a streamline. Okay. And so remember, the streamline coordinate is given by S. So the streamline coordinate, you can think of it as just the distance along the path that the particle is riding, right? Remember, the streamline is basically just like roller coaster tracks that the particle is going to ride along, okay? And so S is just a distance along that track. Okay. And so where we left off, we were characterizing the forces on this particle. Okay? So on the one side right here, we have a pressure force. And so this pressure force, the way that we characterize it was we have our central pressure minus the derivative of the pressure, okay? Because even though we know the pressure at the centroid of the particle, that pressure can change as soon as we move because this pressure is kind of a dynamic thing now. Because remember, we're in fluid dynamics, okay? And so the pressure on the left-hand side of the box, or the force, sorry, is going to be the pressure multiplied by the area of that face, okay? And then the pressure on the other side, we'll call this F press 1, we'll call this F press 2, okay? This is going to have a similar expression, so we're going to have P minus dP ds times delta S divided by 2 times delta N delta Y. Okay. Oh, plus, sorry, because that's on the other side. Okay. And so those are the two forces that are acting in that direction. Okay. And so those are the pressure forces. And so the other force that we need is the weight. Okay. Okay. And so the weight, just like, you know, all weights, is going to point vertically downward. Okay. Oh, sorry, there's a question in the chat. And so does N stand for normal in D? And that's absolutely right. Yeah, so I use the symbol N because it's normal to the streamline. So I use S for the length along the streamline and N for the distance normal to it. Okay. Okay. And so we have a weight that points straight down. But in this particular case, you know, we're going to be summing up the forces along the streamline. Okay. And so what I'm going to do is I'm going to break up the weight into two different components. Okay. So I'm going to have a component that's along the streamline. So it's going to be kind of like this. Okay. And then a component normal to the streamline. Okay. Okay. And then we're going to define this angle right here as theta. Okay. And so just like we did with the hydrostatic forces, we're going to define a triangle to kind of help us out with this guy. Okay. And so if we if we want to sum up the forces along the streamline, we need to find the component of the weight that's along the streamline. Okay, and so that's going to be computed with this. Okay? So we'll call it WS, and WS is going to be a minus weight. So I'll call W weight as W, right? And then we'll multiply this by sine theta. Okay? And so the weight, the reason we're multiplying by sine theta is the weight normally goes vertically down, but we want to get the component that's straight into that, that goes along that streamline, because this weight is a vector, and so we can break up that vector into its different components. One component that's going to be parallel to the streamline, which is what we have right here, and then another component normal to the streamline, which we're going to just ignore at this point. Okay? And so now that we have the pressure forces and the weight, we can sum up all the forces in the streamline direction and set it equal to mass times acceleration. Okay? All right, any questions on this guy before I turn the page? This is just kind of a review plus a little bit more from last time. Okay. Okay, so now that we have all our forces quantified, let's go ahead and sum them up. Okay. And so we're going to sum up the forces in the streamline direction. Okay. And thanks to Newton's second law, we know that this is going to be equal to the mass times the acceleration. Okay. So first, let's consider the pressure forces. So our pressure forces, let's do F press 1. So F press 1 is P minus del P del S, okay, times delta S divided by 2, okay, multiplied by the area. Okay. And so that's pointing in the positive streamline direction. So this entire term is positive. Okay. And then opposing that will be the pressure on the other side. So we have P plus del P del S, delta S divided by 2, okay, del N del Y. Okay. And so since that other pressure force on the right side of the particle is kind of opposing it, that's why we have this minus sign here. Okay. And then finally we have the weight. So the weight's actually going to be opposing the motion of the particle as well. And so what we're going to have is the following. So we have the weight, or maybe I should have plugged this in on the other side. So our weight's going to be given by our specific gravity, or specific weight, sorry, which is, I'm going to put it in terms of density and gravity, okay? And then we're going to multiply this by the volume of the particle, okay? So this entire guy is weight, okay? So weight is just the density of the fluid multiplied by gravity multiplied by volume, okay? And then we have sine theta, okay? And so all we did at this point was we just took all the forces, all three forces that we found on the previous page, and just added them all up, respecting their signs and saying it equal to MA. Okay. Okay. And so before we can actually start working with this, and we can start simplifying, let's substitute in for mass and acceleration. Okay. So mass is pretty simple. So mass is simply just going to be the density of the particle multiplied by its volume. And so remember, since we have a particle that's a box, its volume is just going to be just all the length dimensions multiplied by each other. So delta S times delta N delta Y. Okay. And then the acceleration, we're going to use the expression that we came up with last time, where we put this in terms of velocity and the derivative along the coordinate. Okay. So this is going to be du ds times u. Okay. And this is from last time. Okay. And so what we're going to do next is we're going to plug all these guys in for the mass and the acceleration, cancel out a bunch of terms, and then we'll get something that's going to get us pretty close to our Bernoulli equation. Okay. Right. Okay. So the question is, you want to see the formula for the weight? Absolutely. Yeah, so so I just described the weight as just W here, but then when you actually compute it, the weight of this particle is just going to be the density times gravity times the volume of the particle. And then we're only considering the component parallel to the streamline, so that's why we multiply by sine theta.
Right. Thanks.
Yep. All right. Any questions on this guy before we move on?
Yeah. Can you show me how the normal to the streamline looks?
You mean the force is normal to the streamline?
Yeah.
Yeah. So right now, the only thing is the weight, and so the only force that's normal to the streamline is actually the weight times cosine theta. Right?
I see. Okay.
So this is equal to rho g delta s delta n delta y cosine theta. Yeah, so this is actually important when you're considering rotational dynamics. But for this, we're just gonna ignore it. We're just gonna assume that it's there, but it's not important for the Bernoulli equation. Okay, and so let's actually, just because we have everything here, and I don't want to rewrite everything, let's start canceling some terms. Okay, and so the first thing that we note is that we have a p multiplied by delta n delta y positive. And then we have a minus p delta n delta y, right? And so those two terms are going to cancel out. So we can just cross those guys out. Okay. Next thing that we have is a minus dp ds, ds over 2 delta n delta y, and a positive dp ds delta s over 2 dn dy. And so these two guys are going to combine together. And then, we can get rid of that 1/2. Okay. And then I think everything else we'll do on the next page. Okay? But I just wanted to eliminate that pressure just because it's going to be obnoxious to keep around. Okay. Okay. And so let's plug in everything from our equation. So the first thing we have is mass times acceleration, and so we have mass is density. And at this point, it's going to get confusing between density rho and pressure. So remember, my pressure has a little ponytail. So kind of always remember that little ponytail. And so since this P doesn't have a ponytail, this is density. Okay. And so that's our mass. Okay. And then we have our acceleration. Okay. And so this is going to be equal to minus dp ds times the volume, so ds, delta s, delta n, delta y. Okay. And then minus the weight, so we have rho g, delta s, delta n, delta y, sine theta. Okay. And so all I did there was like just cancel out the pressures like we did before, and then plugged in all the other guys. Okay. Okay. And so the nice thing about this expression is that every single term here has a volume, volume, volume. Okay. And so we can just cancel that guy out. And so now we can save ourselves a lot of writing. Okay. And then we end up with rho du ds times u, which is equal to minus dp ds minus rho g sine theta. Okay. Right. And so through the magic of algebra and canceling lots of terms, we're at like a relatively simple expression. Okay. Okay. So we're getting close, but the one guy that's kind of weird here is this sine theta, right? Not weird in the sense that he doesn't belong, but he's not really put in terms of variables for all the other guys. And so to replace this sine theta, so we want to replace this basically with variables that we can actually work with for the other guys. Okay? And so to replace this, I'm going to draw just a triangle. I guess I didn't need to draw the coordinate axes. Okay? Okay. Or maybe I did. And so let's say that we have the coordinate axes, and in this case, it's just because of the geometry of the problem, we have an x-axis on the bottom and a z-axis on top, because we've already kind of decided that the y-axis goes into the page. Okay. Okay, and so if the length of this triangle is ds, this is just some arbitrary triangle. So ds would be some distance along the streamline. Okay, we can call the vertical side of this triangle, we'll call it dz, and so we can call the horizontal part dx, although we're not really going to use it. And so we can use our trigonometry, and we can say that sine theta is equal to, if we go back to our SOHCAHTOA, so sine theta is going to equal to the opposite divided by the hypotenuse. And so the opposite side of this angle is going to be dz, and the hypotenuse is going to be ds. Okay? And so let's replace our sine theta in with dz ds. Okay? And then we get rho du ds times u is equal to minus dp ds. Okay, minus rho g dz ds. Okay. And so you're probably wondering, why did we do that? So, we had something familiar, which was sine theta, and now we have a derivative which looks kind of scary. Okay. But the reason we did that, use orange, is that now we have ds in the denominator here, okay, which is nice because now we can, what we can do now is that now, since all the derivatives are of the same form, we can replace all these partials, because right now we have these partial derivatives, which is why we have that curvy d. What's the term for it? We can replace these with regular derivatives. Okay. And then if we replace those with regular derivatives, one thing that we can do is we can integrate the entire equation in terms of s. And so by integrating with s, then we're going to get rid of all our derivatives, and then we'll arrive finally at our Bernoulli equation. Okay, any questions here on how we cancel the terms and why we replace the sine theta? Okay. And so actually, one thing that I'm going to do before we actually integrate is first thing that I'm going to do is work on this term. Actually, now that these are regular derivatives now, so we'll do du, regular d, ds times u. Okay. Right. And then I'm going to do like a reverse, kind of like a reverse product rule here, or reverse chain rule. Right. And so what I'm going to say is that this is equal to 1/2 d ds of u squared. Okay? That is chain rule, actually. So it's a reverse chain rule. Okay. Right? And so the reason we do that is just to make the integrating just a little bit easier. Okay? And so reverse chain rule is kind of a trick that's, if you haven't seen it in a previous class, it's kind of abused a lot in kind of applied physics classes like fluids. It's kind of abused a lot, but it's not really taught in math classes, because in math classes you're taught to go this way. You're taught to use the regular chain rule, but the reverse chain rule is really useful for derivations like this, because it helps you get terms in more convenient forms. Okay? And so if we plug that in, we get rho times 1/2 d ds of u squared. Okay? This is equal to minus dp, p with a ponytail, so this is pressure, minus rho g dz ds. Okay. All right. And so now that we have it in this form, let's divide by density. Okay. And the only reason we're doing this is because it gets the Bernoulli equation into the form that it's typically in. And so if we divide by density, we have 1/2 d ds u squared is equal to minus 1 over rho dp with the ponytail ds minus g dz ds. Okay. And so now that we have it in this form, we're ready to integrate. Okay. And remember, whenever you integrate, you have to know what variable you're integrating by. And so in this case, we're integrating with respect to s. Okay. And so what that's going to do is it's going to cancel out these derivatives. Okay. Right. So we'll leave the pressure alone, actually, and I'll kind of explain why in a second. But once we do that, we have 1/2 u squared is equal to minus integral of 1 over rho dp ds ds minus gz. Okay, close to jz, but this is his off-brand cousin gz. And so this guy actually right here, this is actually one form of the Bernoulli equation. It's not that convenient for calculations, but this is one form of it. Okay. All right. Any questions on how we took the steps in order to get here? Okay. So let's explain why I didn't perform this integral right here. Okay. And so the reason I didn't perform this integral is because of this guy, okay? The density. And so, you know, what can happen in a fluid sometimes? So the question is, why is there an extra ds? Is because we're performing an integral, right? And so since we're performing the integral with respect to s, we have to have a ds there just to tell us that we're integrating with respect to s. Yeah. A lot of times, like in books and stuff, this is usually left out, but you need to put it in there just so you know what you're integrating for. Yeah. Okay, so the density. So what can happen sometimes is, you know, because remember, fluids are both liquids and gases. And so if you have a gas, what can happen is that as you move along the streamline, or as you go with the flow, the density can actually change. And so, you know, if you're integrating a quantity with the density along the streamline, you know, you can't just integrate it straight out or assume that it's a constant, because that density might change. Okay. And so for fluids where the density changes throughout the flow, those have a very special name, and so those are called compressible flows. Okay. And so most of the time, your compressible flows will be things like gases, like air, or nitrogen, things like that, or, you know, they can change their density or they can change their volume very, very easily. Okay. So that's kind of important to know. So we'll do a little bit of compressible flow at the very, very end of class. But for now, you know, what we're going to assume is that the density is just going to be constant. And so we can bring it out. And so those flows are actually called incompressible. So that actually brings us to our third assumption that we're going to do for Bernoulli. Okay. All right, so the question is, pressure might change along the streamline, but are there cases where the pressure doesn't change along the streamline? Yeah, there definitely is. So pressure most of the times will change along the streamline, just because pressure is kind of the driving force that drives flow a lot of the time. You know, just kind of naturally. But you can see here there's, and you know, we'll get to this in a bit, but there's another force here that can drive flow, which is gravity. So if you have gravity here that's driving your flow, you know, downwards, like for a waterfall, you can have the same pressure upstream of the flow and downstream, because there's no need for a pressure difference to drive that flow, because gravity is basically doing all the work. And so the places where you don't see a pressure gradient, oftentimes you have gravity that's driving the flow. That's usually the most common place. Yeah. Okay, so if we assume incompressible we assume that it's incompressible. We basically arrive at the final Bernoulli equation. Oh, one thing I forgot to add here is that there's also going to be, since we're doing an indefinite integral, there has to be a constant of integration c. Okay? And so that's actually going to be important. Okay? And so if we assume incompressible and we move some of the terms around, then we arrive at the final form of the Bernoulli equation, which is P with the ponytail pressure divided by the density plus 1/2 u squared plus gz is equal to constant. Okay. All right. And so this is our Bernoulli equation. Right. And so this is going to be the one that you're going to be applying for all your problems. Okay. So it's basically a sum of three different terms. So we have one term which is the pressure, okay, one term that is the velocity, and one term that is the gravity, and all this has to be constant. Okay, and so there's some very important kind of physical interpretations of this, but I think it's been a while, so I think let's do an example first, and then we'll do that. But before I do that, let's go over kind of the most important point of Bernoulli, which is the assumptions. Okay. And so to get to here, we actually applied 4 different assumptions. Okay. And so those kind of go back to the previous lecture, but let me just summarize this here just so you know. Okay. Okay. And so the first assumption that we made kind of at the very beginning is that we're going to ignore viscosity, right? And so we're basically going to assume that the viscosity is either really small or is just really negligible compared to the pressure and the gravity forces. Okay. Okay. The next assumption that we made was that the flow was steady, so we don't have things changing with time. Okay. And so our third assumption, which is at the top here, is we're going to assume that the flow is incompressible, right? And so the incompressibility assumption basically allowed us to assume that the density was constant, and we can just pull it out of the integral. Okay. And the fourth assumption is something that's kind of been implicit in this entire derivation, and that's the fact that we can only apply this along a streamline. And so if you're going to apply the Bernoulli equation, you can't you can't go across the flow. Like you can't go from one bank of the Mississippi River to the other side and apply Bernoulli that way, because that's not where the fluid flows. And so the only way that you can apply the Bernoulli is in the same direction as the Mississippi River. So you can only go down the river, not across it. So you have to follow basically the path of the flow when you're applying Bernoulli. Okay. All right. Any questions on this before we jump into an example? So the question is, does assumption 3 mean that rho might change? So actually, in this case, if we assume that it's incompressible, rho doesn't change. So it's actually going to be constant. So it's going to be it's just going to be a constant throughout the flow. Yep. Yeah. So that's something we're going to assume for most of this class. We'll ease up that assumption near the end when we do compressible flow. Okay, so let's do an example just so you can see how this is applied in practice. Okay? So it's a relatively simple example, but I think it's pretty nice. Okay. Okay. So let's do an example that kind of has to do with building design actually. And so if you're designing a building, what you have to design for is you have to design for the fact that the building is going to support some weight. Oh, sorry, there's a question. So the question is, can I explain compressible, incompressible again real quick? Yeah, definitely. So compressible, what that means is based on like the word states, is that you can take your fluid and you can kind of compress it into a smaller space, and you can actually do that, and that's going to be fine. Okay, you can either compress it or you can expand it, and the volume is going to change with the exact same amount of mass in the fluid. Okay. And so, you know, as you change the volume, or as you you imagine you have a balloon full of gas and you kind of compress it into a smaller space, right? The amount of air or the amount of gas in there is going to be the same, but if you pack it in more, then the density is going to change. And so for our purposes, you know, when we say compressible or incompressible, compressible, what that means is that the density can change because, you know, we can compress the air into a smaller space or expand it. But incompressible means that the density is not going to change. So like if you take a water balloon and you can try to squish it as much as you want, you might be able to deform it. It might deform in different ways, but it's never going to change its volume. And that's basically what it means to be incompressible. Does that make it a little bit more clear on what that means? Yeah, okay. Okay, so let's do an example for the wind blowing against a building. So another thing you actually have to design for, especially if you're doing like a really tall building, is the fact that wind is going to hit your building, and that's going to actually cause some force. And so part of that building design is you have to compute, you know, how much force is the wind going to put on my building. Okay? And so let's draw a rectangle, and this rectangle is going to be our building. Okay, and let me draw 2 points. Okay, so we'll call this point 1. We'll call this point 2. Okay, and let's say that wind is coming from the left at point 1 and hitting the building at point 2. Okay, and we know that at point 2, the velocity is going to be 0 at point 2 because the wind is basically going to come from the left. It's going to hit the building, and then the wind's just going to be like, it's just going to like tackle the building, and then it's just going to kind of stop right there. So we know that at the point 2, the velocity is going to be 0. Okay, and the velocity at point 1 is u1. Okay. Okay. And so what we want to do is we want to use Bernoulli to find basically the pressure at point 2. Okay. Because as we know, as we kind of reviewed at the beginning of class today, if you know the pressure, then you can compute the force from that just by multiplying the pressure times the area of the face. Okay. All right. Any questions on just the setup of the problem? Okay. Okay, so let's apply Bernoulli here in order to solve for this problem. Okay, so the first thing that we should check is we should check all of our assumptions. Okay, and so first of all, our first assumption is that we ignore viscous effects. So we can just kind of just say that we're going to ignore it. And for airflow, you know, that's usually the case. Okay. Number 2, that the flow is steady, and so we've been given no indication from the problem that the flow is going to change with time, so that one's okay. Third, that the flow is incompressible. So this one might be a little bit hard, you know, to justify because I just got through saying that gases can be compressed. But for this particular problem, let's just assume that the air is going to be incompressible. So that's going to be an assumption that we're going to make. Okay. And usually, if the velocities aren't too high, that's usually a very fair assumption. And then our last assumption is that the flow is applied along a streamline. So that's definitely the case here because we're following the flow from point 1, which is where the wind starts, and then we're going to end right when the wind hits the building. So that's exactly in the path of the flow. Sorry about that. I punched the microphone accidentally. Okay. And so now that we've checked basically that we can apply Bernoulli, let's go ahead and do that. Okay. So remember, our Bernoulli equation is given by this guy right here. Okay. And so we have P with the ponytail, divided by rho, plus 1/2 u squared plus gz has to be constant. Okay. And so if this quantity has to be constant, what we can do is we can compute Bernoulli at point 1, and then compute Bernoulli at point 2, and these two guys have to be the same. Okay. And so first, let's write out Bernoulli at point 1. So Bernoulli at point 1, we'll call it P1 divided by rho plus 1/2 u1 squared plus g Z1. Okay. So those are all the conditions at point 1. So we have the pressure at point 1, the velocity at point 1, and the height at point 1. Okay. And this has to equal to the same conditions at point 2. So we have P2, P with the ponytail, divided by rho, plus 1/2 U2 squared plus G Z2. Okay. Right. So this is Bernoulli at point 1. And this right here is Bernoulli at point 2. Okay. And so this is how you're going to set up basically all your Bernoulli problems. Is because this Bernoulli sum here is constant, we can compare the Bernoulli sum at 2 different points and set them equal to each other, and then use that to solve for all the variables that we want. Okay. Okay. So let's start applying some conditions from the problem, because we know some stuff about this flow. Okay. And so the first thing that we know is that because the wind is hitting the building at point 2, then U2 is going to be equal to 0. And so we can go ahead and just cancel that term right there, because we know U2 is equal to 0. Okay. Okay. And so the next thing that I'm going to cancel is the height terms. Okay. Okay. And the reason I'm going to cancel the height terms is the fact that, as we go from point 1 to point 2, we're at the exact same height. So we're just going completely horizontally. So if Z1 is equal to Z2, then those 2 terms are just going to cancel out. Okay. And so after we perform those cancellations, what we're left with is P1, P with the ponytail, divided by rho, plus 1/2 U1 squared is equal to P2, P with the ponytail, divided by rho. Okay. Okay. And then what we can do in this problem now is we can just solve for P2 minus P1, which is the pressure difference at the building compared to over there on the left. Okay, so any questions on how we set up this problem? We set the Bernoulli sums equal to each other, and then we canceled the terms. Does that kind of make sense to everybody?
So now we're solving for P2 minus P1?
Yes. Yeah, so the pressure difference between the building and the, you can consider like atmospheric air. Okay. So let's go ahead and do that. And so to solve for that, I'm going to multiply both sides by the density, and then move P2 minus P1 onto one side. And so what we get is P2 minus P1, both P's with the ponytail, is equal to 1/2 rho U1 squared. Okay. Right. And so from this expression, we can say that the pressure difference between the building and the atmospheric air is going to be directly proportional to the velocity of the air squared. Okay? And so the faster that the wind is blowing, the more pressure that you're going to have, right? And so intuitively, that makes sense. So if you have like a hurricane force wind blowing at your building, that's going to produce a lot of force versus like a gentle breeze, which is not really going to do anything. So the faster your flow is, the more force that you're going to feel. Okay? And oftentimes, because we pick point 1 to be so far away, this could be like something like atmospheric pressure, which is something that you know. And so, basically, in order to decelerate the flow from U1 all the way to the building, which has a 0 velocity, the pressure has to increase. All right, any questions on how we got this result? Okay. All right, so let's talk about, now that we've kind of seen the Bernoulli equation in action, let's talk about just different ways that we can actually interpret the equation itself. Okay. And so these are actually really important, because I think these physical interpretations give you kind of the intuition that you need to apply this kind of more easily into the future. Okay. And so far, when we derived the Bernoulli equation, oh, so question. So just to double check, more pressure equals faster flow. So it's not that more pressure equals faster flow. A bigger pressure difference means faster flow. Right? And so just pressure by itself doesn't produce flow. We saw that with our hydrostatic cases, right? Like, just because you have pressure, you don't have flow. But if you have differences in pressure, that doesn't have anything to do with hydrostatics, then that can produce flow. So if you have two horizontal places and the pressure difference between them is really high, that's going to drive the flow. Okay. So far, once we when we derived Bernoulli equation, we derived it in terms of Newton's law. So we used force is equal to ma, basically, right? And so that's one way that you can interpret Bernoulli equation, is that Bernoulli basically represents all the different forces that can drive a flow. So we have the pressure term, and then we have the gravity term, and then that results in some velocity. But remember that velocity came from our acceleration. Okay? And so that interpretation is fine. So that's kind of like the force or the Newton's laws interpretation of Bernoulli. But I think this one kind of makes a little bit more sense to me. And so another way that you can interpret Bernoulli is kind of like from a conservation of energy perspective. And so to kind of remind you of this, let's recall the work energy principle from physics, right? And so the work energy principle states that the work done on a particle by forces acting on it is equal to the change in kinetic energy. Okay. Whoa. Okay. And so we can actually apply this interpretation to Bernoulli. Okay? And so let's take basically the same expression here, where we take the Bernoulli equation at 2 points. Okay? Okay. And so we'll compare the Bernoulli equation at 2 different points. And what I'm going to do is I'm going to rearrange the terms a little bit. Okay? And so the way I'm going to rearrange the terms looks like this. Okay? And so let me use different colors here. Okay? So the first term that we have will be a change in pressure. Okay? And so the next term that we have will be a change in height. Okay? And then all this is going to be equal to a change in kinetic energy. Okay? Okay? And so let's, this is basically just the same Bernoulli equation that I had on the previous page. I just rearranged the terms a little bit to make it more convenient for this interpretation. Okay? And so let's group each of these terms that I've colored, and let's label them, and let's describe them and put them in terms of the work energy principle that I have up there. Okay? And so this P1 minus P2, one way that you can interpret this is the work done by pressure forces okay? This term right here, this is the work done by gravity. And then finally, this guy over here, this is our change in kinetic energy. And so if we rearrange the Bernoulli equation in this form and then kind of put it within the context of the work energy principle, we can say that, you know, any change in kinetic energy that a fluid experiences, ignoring viscous effects and everything like that, the only way that the kinetic energy can change is due to work done either by pressure forces or by gravity forces. Okay. And so this right here is kind of my favorite interpretation of Bernoulli, because it kind of makes intuitive sense, because any flowing fluid will have some kinetic energy because it has velocity, and just changes in that velocity will be accomplished by you know, work done by the different forces. Okay. Right? Any questions on this? Okay. Okay. So let's do just one more example, just to kind of illustrate that interpretation. And so let's say that we have a syringe of fluid and we're just kind of squirting it upward. Okay. Okay. And so the geometry looks something like this. So we're, you know, we have a syringe and we're squirting it upward like this. So let's consider 3 different points. So let's consider one point at this at the plunger. Okay. We'll have another point at the nozzle, and then we'll have another point up here. Okay. And so I'm not going to put any numbers on this. So this is just kind of an intuitive example. And so let's characterize, you know, all those 3 different energies that we talked about on the previous page. Okay. So let's talk about the kinetic energy of this flow. Let's talk about the gravity. And then finally, let's talk about the pressure. Okay. And let's just characterize their relative magnitudes from each other. And so we'll have 0.1, 0.2, and 0.3. Okay. And so basically what I'm going to fill in here is either a 0, where if that energy is going to be 0 at a particular point, it's either going to be, or it's going to be either 0, small, or large. Okay. Okay. And so let's talk about 0.1 first. So 0.1 is yeah. So z is a change in height. Okay. So 0.1 is at the plunger, and so, you know, this plunger, we're applying a force here, right? And so at 0.1, what's happening is that, you know, the plunger is moving, although it's kind of moving slowly, because, you know, if you ever used a syringe before and you push it out, you usually push the syringe fairly slowly. And so because the 0.1 is attached to the plunger, it has some kinetic energy because the plunger is moving. It's just not that much. So so let's say that the kinetic energy of 0.1 is going to be small. Okay. All right. And so now let's consider the kinetic energy at 0.2. So at point number 2, the fluid is just coming out of the syringe. So it just went from this big tube down to like a tiny needle, right? And so in order to get to that tiny needle, the velocity has to be really large in order to get through that. Sorry, I keep punching the microphone. And so the kinetic energy at 0.2, because the fluid is kind of squeezing through that tight orifice, this will be large. Okay? So the velocity has to be really big at 0.2. And so at 0.3, basically the fluid has basically reached its height. And so, you know, if you kind of remind yourself, or if you toss a ball up and the ball reaches the top of the height, you know that at the top of the throw, the ball is going to have 0 velocity, right? So if it has 0 velocity, then its kinetic energy will also be 0. Okay. And so that's the kinetic energy. So now let's talk about the gravity forces. Okay. And so so the gravity forces are directly proportional to height. Okay. And so basically we can just compare all the heights of the different pieces. Okay. So point number one is the lowest point in our syringe. So this is going to have 0. You can kind of think of it almost as like potential energy. So it has 0 potential energy there. At point number 2, it's midway up, so it's going to have a small amount of gravity energy. At the top, it's at its peak, so it's going to be large up here. Okay. 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 And so now let's characterize the pressure. So the pressure here, it's a little bit difficult to, a little bit more difficult because it's not as intuitive as the kinetic or the gravity. But you'll as we go through the fluid, this fluid dynamics course, you'll gain some intuition for this. Okay? And so first of all, let's characterize the pressure at point 1. And so point 1 is right next to the plunger, right? So the plunger, you're applying the force, right? And so in order to basically drive the flow upwards, the pressure force has to be high at point 1. Okay. All right. And so point 2 and point 3, they're actually going to be the same pressure. And so because point 2 and point 3 are exposed to atmospheric pressure, we can say that the pressure forces are going to be 0 over here. Okay. Okay. So this was just kind of a simple example. So we put no numbers, but it's just mostly just to start to give you guys some of the intuition of, these 3 different categories of energies: kinetic energy, gravity energy, pressure energy, and how to characterize them within a flow, and that there's always going to be a balance in between these 3 things for fluid flow situations. Okay. All right, are there any questions on this?
So this was just basically the categorization of each force.
Exactly, right. Mm-hmm. Okay, so the question is, can I explain the pressure column again? Sure. So the pressure column, the first thing we have to do is point 1. So point 1 is basically at the plunger. So since that's where we're applying the force, that force is basically driving the flow. So the pressure, remember, is just force divided by area. So the pressure has to be large at the plunger. Okay, so that's the first one. And so the reason the pressure at points 2 and 3 are 0 is the fact that once the fluid leaves the plunger, it's basically going to be exposed to atmospheric air. And most of the times, just for the sake of computation, we assume that atmospheric air has a pressure of 0. So that's why pressure forces are going to be 0 at points 2 and 3. Mm-hmm. Okay, so I do want to cover maybe one more point before we leave, and that's this idea of a stagnation point and a stagnation pressure. So stagnation is a very important concept in fluids, okay? And it's a very long word, but all it basically means is that the flow has 0 velocity. So if you're familiar with the term stagnate, then basically stagnation is just, the same thing. So stagnation, for our purposes, what it means is that the velocity is 0. And so just like we saw in the building case, our building example from before, for cases where the velocity is 0, usually you're going to have a pretty high pressure there because the flow is basically going from something really, really fast to something that's 0. Okay. So before I turn the page, are there any questions left on this page right here? Okay. And so if stagnation means that the velocity is 0, a stagnation point is basically just any location where the velocity is going to be 0. Okay. And so, the other important term to note here is the stagnation pressure. Okay. Okay. And so the stagnation pressure is nothing more than just the pressure at a point where the velocity is 0. Okay. Okay. And most of the time, the stagnation pressures are usually very important to know, is because the stagnation pressures are usually where the pressure is highest in a fluid flow situation. So these are usually the places where pressure is highest. As you can imagine, that's usually something of intense kind of engineering interest, is seeing where your pressures are max. And so if we go back to our building example, we can say that P2, where P2, remember, that was the pressure on the building. So this is our stagnation pressure. This was equal to P1, which was the upstream pressure, plus 1/2 rho U1 squared. Okay. And so here we're ignoring just any kind of height differences in between the 2 points, which most of the times is okay, because pressures most of the time will dominate your expression. Okay, and so if we kind of connect this to our interpretation for energy, one way that you can interpret the stagnation pressure is that all the kinetic energy that you had when the flow was really high or the velocity was really high, all that gets converted to pressure energy. Okay. Okay. And so at the stagnation, we know that velocity is going to be 0. So any kind of kinetic energy that you had before, all that's going to be converted to pressure. And that's why the pressure has to rise at these stagnation locations. So these locations, stagnation points, stagnation pressures, are going to be really important for a lot of flows. And if you're doing any kind of aerodynamics, that's going to be really important. Okay. All right. Any questions on this? Okay. Okay, so just another example for stagnation point is, like, say we have a, well, let me draw the figure first, and you can interpret it in lots of different ways. Okay, so let's say that we have an object. Okay, in this case it's an egg. Okay, and then we have flow that's going around it. Okay, so I'm gonna draw the streamlines. Okay, and then there's gonna be one streamline that comes right up to the egg, and it's going to just basically hit the egg straight on, right? So this right here is your stagnation point. Okay. And so your stagnation point, that's basically where the flow is going to be 0. So most of the time that's a streamline where the flow basically just hits the object kind of just head on, right? And so this right here is a stagnation streamline. Okay. And so, you can interpret this figure in a lot of different ways. So kind of the first thing that comes to mind, or at least maybe for me, is that you can look at this as kind of an airfoil. So this is like an airplane wing that's kind of flying throughout the air. And then for every airplane wing, there's always going to be a stream of air that's going to hit your wing kind of right on the front. And so that's going to be really important, because that's going to be your stagnation streamline, your stagnation point. And that stagnation pressure there it's a big consideration for how you're going to design your wing. So that's one way that you can interpret this. And so another interpretation is that this is like a babbling brook, or like a river, and you have a rock or a boulder that's in that river, and you have water that's kind of hitting that boulder right there. So the pressure that develops on that boulder is due to the stagnation point. So basically anytime you have a solid object that's within a flow, there's always going to be a stagnation point, and there's always going to be a stagnation pressure on that flow. Okay. And the way that you compute that stagnation pressure is through Bernoulli. Okay. All right, any questions on this?
Professor, so the pressure at that point will be the highest in considering like the entire system?
Yes, at least for within this drawing right here, yeah. And so if you consider just the flow around this, because there's no other location here where the velocity is going to be 0, the pressure is going to be highest at that point, just at least for this drawing right here.
Okay.
Yep. Okay. So that's all we got time for this week. So we're basically at 9:45. So just a weekly reminder. So we had 2 lectures this week. So the minute paper for this week is up on Canvas. I keep wanting to say titanium. And so remember, if you have the time, definitely fill that out. Basically, it's just going to ask you to summarize what you thought was the most important point this week, what was the most confusing, and what you just any feedback that you have for the class. Okay? And so remember that information is really valuable for me to basically improve this class, especially as we go through the semester. So please fill that out if you have the chance. But if not, I'll see everyone on Monday. So have a great weekend. Thank you guys for tuning in, and I'll see you next week. Going back to the homework for 3B, YC is equal to Y over 2, and HC is H over 2. Correct. Yes.